Okay, in our previous video, we looked at covalent bonding in a bit more detail. Now we're going to look a little bit closer at ionic bonds. And we said that in ionic bonding, one of the key features is that we don't have any sharing of electrons. And at the last video, at the very end of it, we said that ionic bonds are going to arise whenever we have elements with vastly different electronegativities. So if you consider something like sodium and fluorine. Okay, now in both cases here we're looking at atoms. Okay, if we look at the Lewis structure for each one of these, okay, we see that sodium is going to have one valence electron. Fluorine, we know, is going to have 7 valence electrons. Now, if you consider the nature of these two elements, you know that sodium, being a metal, is on the far left-hand side of the periodic table and has a tendency to form cations, whereas fluorine, being on the right-hand side of the periodic table, has a tendency to form anions. And we know that that's because by gaining or losing electrons, these things can get a valence shell that looks a whole lot like the closest noble gas. So we know that sodium is perfectly happy losing an electron. So we can show that happening as sodium being converted to sodium plus 1 electron. And we know that fluorine likes to gain 1 electron, because by gaining that 1 electron, it's going to have its full octet. So we wind up with fluoride, which is negatively charged. Okay, so initially what's going to happen is when you mix a sodium atom with a fluorine atom, is that the sodium atom is going to transfer its electron to the fluorine to make fluoride. Okay, so we have our cation and we have our anion. Now, sodium still wants to feel some kind of negative charge to make it feel neutral again, but it's not going to just tear an electron back away from the fluorine. So instead, the sodium is far more content with just hanging out next to the fluorine. Okay, and by being next to the fluorine, that's balancing out the charge without it having that 1 additional electron in its own valence shell. Now, like I said, we try to fit all these bonds into 2 categories, but really these 2 categories are just extremes of a spectrum. Okay, so the extreme on one side is going to be the covalent bond. And then on the other end of that spectrum, we have the ionic bond. Okay, and everywhere in between is what we call a polar covalent bond. And the thing that distinguishes whether or not you have a covalent bond or an ionic bond or a polar covalent bond is the difference of the electronegativities of the 2 atoms involved in the bond. Okay, so remember, we said some elements are more electronegative than others. In other words, they want electrons more. Okay, so that difference in electronegativity is what defines the type of bond. And again, this is a spectrum. It's a continuum, so there's going to be spots where it's going to be a little bit less than obvious what type of bond we're going to have. The only time that we have an absolute type of bond is when we have a nonpolar covalent bond. Okay, that's going to happen when we have a difference in electronegativity, okay, upwards or sorry, equal to 0. Okay, so anytime we have two elements that are exactly the same, like in the case of hydrogen or fluorine, okay, the difference in electronegativity is going to be equal to 0. It doesn't matter what the elements are because, well, they're going to have the same electronegativity. There is one case, though, where we have a bond that is between two non-equal atoms. And that's the carbon-hydrogen bond, where we essentially have a nonpolar covalent bond. The difference is so small, it's about on the order of about 0.4. So then it becomes a question now of what's our cutoff for going from a nonpolar covalent bond to a polar covalent bond, and what's our cutoff going from a polar covalent bond to an ionic bond. I don't want to get caught up in that discussion, just because it's really more a question of what bond is more polar than another bond, or more ionic than another bond. Okay, so for our purposes, let's not get caught up in the actual defining difference in electronegativity, but just recognize that the bigger that difference in electronegativity, the closer we are to being ionic. Okay, so if we have something that's from the far left-hand side of the periodic table and being bound to something on the far right-hand side, like, for example, sodium and fluorine, well, that's going to be an ionic bond. Okay, that's about as far as, well, not as far, but it's a pretty extreme value for the difference in electronegativities. When we start seeing things like maybe a carbon-bromine bond, okay, now that's going to be a more polar covalent bond, or an OH bond. Okay, now we can actually look up values of electronegativity on the periodic table, but there's some general trends that we can make use of that makes our life a lot easier. So let's look at that. Okay, the first thing that will help you remember relative electronegativities is recognizing that fluorine is the most electronegative element on the periodic table. Okay, so that tells us that the electronegativity is going to increase going from left to right on the periodic table and from bottom to top. So left to right, electronegativity increases, and from bottom to top, electronegativity is going to increase. Okay, so if you look at some relative positions of elements on the periodic table, if you were trying to compare, say, a bond between carbon and fluorine versus a bond between carbon and chlorine. Okay, in both cases we have our carbon, right? The difference between the two bonds is the fluorine and the chlorine. Okay, so we know that fluorine is more electronegative than chlorine. How do we know that? Because fluorine is above chlorine on the periodic table. So therefore, the CF bond is going to be more polar because the fluorine is going to be further away from the carbon than the chlorine was in terms of electronegativity. Whereas the carbon-chlorine bond would be less polar. Okay, and again, that is what determines whether or not bonds are going to be polar or nonpolar or ionic. What we're going to do in the next video, though, is we're going to look at applying these Lewis structures that we've drawn in the previous videos to much more complicated molecules. And that'll be the next focus here.